Okay, welcome back, and this is part two of our probability series, of which I intend on going through the entire probability and statistics course in Specialist Maths chapters 15 and 16. Now, I was sort of saying last time that these sort of questions, especially when we're looking at a linear combination, are very common in exam one questions. When I say common, I'm just basing that on a very small sample of sample exams, Northern Hemisphere exams, 2016, 17 and 18 exams. And that's why I will be going through a 2018 exam question. Now, as these things should all come from or be assumed knowledge from methods, but just quickly, I want to point out that the mean is also known as the expected value, e to the x or mu. The variance can be known as the variance of x, or sigma squared. And the standard deviation, of course, is the square root of the variance of x, which also is sigma. Sigma, the Greek alphabet. Alpha, beta, gamma, delta, epsilon, phi, xi, theta, zeta, etc., etc. So now, if we can just go into the expected value of x. Now, what we can say is that this has to really be committed to memory. Okay, it may be on the formula sheet. It may be on the formula sheet. But you should not have to look at the formula sheet to recognize a linear combination of random variables. So let's just get straight into it. X is a random variable with distribution. Mu is equal to 10 and the standard deviation is equal to 4. Let u is equal to 2x plus 3. So find e of u. So first of all, we know that u is equal to 2x plus 3. And we can say that e to the u is equal to e to the 2x plus 3. And if you have knowledge at your fingertips, that would be the same as 2e to the x plus 3. And of course, e to the x is mu, so that's 2 times 10, which is 20, which is, so that's going to be 2 times 10, 20 plus 3, which is 23. Okay, so now we also over here have x and y independent variables with we've got our separate standard deviations and mu's. Find e to the 3x minus y. So e to the 3x minus y is equal to 3 e to the x. Be careful with the sign. It's minus e to the y. And 3e to the x, well, that's mu x over here, which is 3 times 3 times 30, which is 90, minus e to the y, which is 10. So that's going to be 90 minus 10, which is 80. Okay, so there you go. We've just found e to the u, and we've found a linear combination. And it's a real common sort of thing, and I'm going to do an exam question soon to sort of show you. Now, going back to variance, here's a really important thing here. You've got to notice here that this b, if I was to have 20, 30, 40, and then all of a sudden I added 10 to each of these values, then I've got 30, 40, 50. The variance hasn't actually changed. So this whole plus b, okay, is really sort of we don't need to worry too much about it. But what we need to do though is if we have a constant out the front of our linear sort of combination, then it's that a squared. So it's be very careful with that. And the same thing over here, the constant. So we've got a squared and b squared. Okay, so x is a random variable with distribution mu is equal to 10. Let u equal 2x plus 3. Find the standard deviation. So when we're finding standard deviation, I guess you really sort of want to sort of find the variance first. So let's find so first of all, let's find the variance of u, and that is going to be, um, that's going to be the variance of 2x plus 3. Now, as we said, that 3 really doesn't matter. It's this 2, but it's squared. So it's 2 squared, my bad, 2 squared times the variance of x, which is 4 times the variance of x. And since the variance of x, well, we don't have the variance of x with the standard deviation. So the standard deviation is equal to 10, is equal to 4. So therefore, the variance is equal to 16. So therefore, the variance of u is equal to 4 times the 16, which is 64. Now, therefore, we can say that the standard deviation of u is the square root of the variance, which is the square root of 64, which is equal to 8. Hooray! It's not that bad, is it? Now, x, I'm not sure if you even do this in methods. I don't think you do. This sort of linear combination. Maybe because someone can let me know. Now, x and y are independent variables with blah, blah, blah. Find the variance of 3x. So once again, we want the variance of 3x minus y. Now that's equal to, you need to be careful here because if I was to do the expected value, the negative would actually matter. If I square -1, that's going to be positive result anyway. So that's what you've got to be very careful of. So now we want to find the variance of that. Okay, so we've got to say that that's going to equal 3 squared, which is 9, times the variance of x. And technically it's plus the variance of y because it's -1 squared. Okay, so that's going to be, now we've been told that the variance of x is, well, that's the standard deviation of x. So if I square that, that's going to be 4, which is 9 times 4. And the variance of y is going to be equal to 16. 36 plus 16 is 52. And that's our answer. I think it's always a good, whenever you're doing like an exam question or something, put a box around it or something, just make your answer very obvious. Okay, so now let's continue on. Now, look, I've got the theory in the background over here and the stuff that's going to be on your formula sheet if you need it. And if you need to look at your formula sheet, then you probably haven't studied hard enough. And you probably haven't created a good bound reference in the first place, to be perfectly frank. But let's have a look. It says here the theory for independent normal random variables x and y. Ax plus by also has a normal distribution. Use norm CDF, and you should know norm CDF, menu 552. You've got to start getting really fast with these things because, of course, if you can get it done in half the time because you're really good with your calculator, you're going to be less stressed in exams. Now, the thing is, though, if I want the probability of A is greater than B, this is a really useful thing. We basically can say that the probability of A minus B would be greater than 0. So if I had two values, A is 17 and B is 18, okay, clearly at the moment you can say that A is not greater than is not greater than B. Well, the values are not greater than B, but maybe the probability could be. But this is actually a really useful thing, which we'll do later. Problem is with these questions, whether English is your first language or not, is that there's a lot to take in. So I'm going to get my highlighter out because I don't really want to highlight that much. Let's start getting some really important details. The combined takeoff and landing time from Melbourne to Sydney is normally distributed with the mean of 22 minutes and a standard deviation of 3 minutes. The flight time at cruising altitude is also normally distributed with a mean of 1 hour. Oh, be careful. Look, that's 1 hour. That's not in minutes. And a standard deviation of 5 minutes. 5 minutes probably would be more ideal. Find the probability correct the 4 decimal places that a flight from Melbourne to Sydney takes longer than 1.5 hours. So, it's a lot of information to take in, isn't it? So, okay, we've highlighted everything that we need. Now what we need to consider is how we're going to tackle this problem. Well, this is a linear combination of independent, normal, random variables. Why is it normal? Because that they have a mean and a standard deviation. Okay, so I guess doing this, what I think we need to consider is, well, let's sort of start to declare some variables. Well, first of all, we've got like a density function, a probability function. So I'm going to say that the landing time, so I don't know, what would I call that? I'm going to call that, I'm just going to call that L. And that's going to be normally distributed. And it says here it has a mean of 22 minutes. And it has a standard deviation of 3 minutes. But remember, when we write our distribution, we write out our standard deviation squared, don't we? Okay, so let's start. Now it says here the flight time at cruising altitude, blah blah blah, is 1 hour. So flight time, I don't know, let's just call that T. And that's normally distributed. And it says here that the flight time is normally distributed with a mean of 1 hour. Well, you got to be consistent, don't you? It would make sense to do everything in minutes. So that's going to be a mean of 60 minutes. And it says here a standard deviation of 5 minutes. So we're going to sort of say that, well, it's not 5, it's 5 squared, which is 25. Okay, so we're off to a start. Okay, now what we want to find is, it says here we want to find the probability that L plus T, it says here it takes longer than 1.5 hours, which of course is 90 minutes. Okay, and of course we want to work that out. Now, of course, we sort of need to stop there because we're going to do some things. This is a linear combination, so let's do e to the L plus e to the T. And of course, that's equal to 60 plus 22, which is equal to 82 minutes. Okay, so that's and by the way, that's our mu, isn't it? Okay, or we could say that that's equal to e to the L plus T if you wanted to. But yeah, that's our mu. Now the variance. So the variance is of a linear combination. The variance of L plus T is equal to the variance of L plus the variance of T. So it's actually not too bad a question, but a lot of students wouldn't even know where to get started on such a thing. Okay, So now the thing is, though, we don't know what that is. We do know, however, well, in actual fact, the variance of L is equal to 9, and the variance of T is equal to 25. So that's equal to 34. But of course, we don't want the stat. We want the standard deviation of the landing time plus the in-flight time, and that's the square root of the variance, like so. Hope that's making sense so far. Now, we have all the information we need. We have our mu. We don't really need the variance because we need our standard deviation when we're doing these things. And menu 552, let's go ahead and see, and let's go ahead and work this out. Okay, so menu 552. Oh, so we're looking for a value, which is we're looking for the value which is our lower bound. Now remember, our mean is 82. Okay, we don't need to do a standard of normal distribution here. Okay, what is our standard deviation? It's root 34. Now be very careful here. Okay, sometimes you do this 34. I think this one will work okay, but there's some bugs in other ones. Now, we want to start with our lower bound is going to be, we want the probability. Let me read the question again. Where's my piece of paper where I actually wrote it? Okay, so it was 1.5 hours. So our lower bound is 90 minutes and our upper bound is infinity. Now, how do I get to infinity? I go to here. Okay, and let's see, 0.085. 0.085. Now, I want you to think about it. Is that correct? Have I done it correct? Do you agree with everything I've done? Well, let's state an answer. I think it's right. But I told you I'm going to make some mistakes here. But let's actually write it out as this. The probability that L plus T is greater than 90 is, and it says here correct to 4 decimal places, is approximately equal to 0.0850. Okay. And that is that's all she wrote. Now, look, you could do this the standard normal, which means that you would have to sort of go z is equal to x minus mu over, what a waste of time that would be, okay, because when you use your calculator, you don't have to find that. And that would actually mean that we'd have to work out what that z score is, for 90 minutes, okay. 90 minutes, so let's say, so the mu, so 90 minus mu, which is 82, over the standard deviation, which is root 34. Yeah, we'd actually have to work out what that Z score is, and so it'd be a bit of a pain. Don't go wasting your time doing that sort of stuff. Okay, so I hope that made sense, or you might need to pause it, have a look at it again. All right, now here's a bit of a variant sort of example, and I said that this is a difficult question or concept. Note that a random variable can change with every trial. So therefore, if the variance of nx does not represent the variance of n number of x's, but rather the variance of an interval x multiplied by n. Now, it is very confusing. It took myself a long time to get this with Mr. Hodge last year, and we had conversations for about 20 minutes over a coffee. Now, it says here that apples grown in an orchard have a mean mass of 101 grams. Okay, so 101 grams. Let's just get our highlight out. And a standard deviation of 8. So we're looking at apples. Oranges are grown with a mean mass of 190 and a standard deviation of 6. So we're looking at standard deviation. We're looking in grams. We find the mass of the apples and the oranges are independent. It's pretty important, actually. This independent, the masses are independent. A hobbit collects 4 apples and 2 oranges every day. What is the expected weight and the standard deviation of her daily collections? Now, I just want to ask you, is this working correct? Okay, is this working correct here? Is the variance of t, where t is basically we're collecting apple 1, apple 2, apple 3, apple 4, orange 1, orange 2, we're collecting 4 apples and 2 oranges. So is this right? I want you to have a little bit of a think about it, okay? And please explain why or why not, because if you have a bit of a think about it, maybe if you encounter the same thing in the exam, you might be able to think through it yourself. Okay, so I'm going to pause it here. I want you to think about this. I want you to answer this question. Please explain why or why not this is correct. It may be correct, but I want you to think about it. So I'm pausing right now. Okay, so the answer is, well, this is actually incorrect. And the reason being is because each one of these apples is its own unique apple. And so this is incorrect. And it's one of the harder concepts to sort of go through. So really what we're looking at is that T is equal to 4A plus 2O. You know, we don't want that. In actual fact, what we're looking at, if we're looking at the variance of T, okay, we're looking at the variance of apple 1 plus apple 2 plus apple 3 plus apple 4 plus orange 1 plus orange 2. And of course, that would be equal to 4 times the variance of A plus 2 times the variance of O, which clearly is not what we have up here. Okay, so it's a tricky concept. It's a really tricky concept. It comes up in exams. It's something you have to be very aware of. So I'd be putting this sort of thing in your bound reference. So look, the variance of T, not that we need to really that's equal to 4 times the variance of A, which is 4 times 64 plus 2 times 36, which is equal to 256 plus 72, which is what, 328. You know, if we were to ask for the expected value though, then the expected value is A1 plus A2 plus A3 plus A4, sorry, plus O1 plus O2. That's a little bit different because that's going to be 4 times the expected value of A plus 2 times the expected value of O. Which is, what is that going to be? If I have a look, we're looking at 101 and 190. So that's going to be 101 times 4 plus 190 times 2. Doing that in my head, what's that? 380 plus 380 plus 404. So it's going to be 784 grams. That's going to be the expected value. If I pick out 4 apples and 2 oranges, that's going to be the expected value. So no, it is not correct. This is not correct. And it is something that has, I think, come up in an exam once. All right, now let's continue with this. Now we'll start to look at the sample mean and start doing some simulations. And I want to talk some theory again. Now I talked some theory in the last class, or the last lesson. First of all, sample means. The concept of the sample mean is the sample mean has, we call it X bar. It means that we've taken a sample. Okay, we've taken a sample of say 5 and 10, and that's a random variable where x is a random variable with a mean mu and standard deviation of sigma, which is exactly what we've discussed before. If the simulator is repeated enough, we'll sort of illustrate the fact that the sample size actually has an effect on the standard deviation. And this sort of is what we were talking about, the central limit theorem in part 1. So what we're going to talk about is basically population samples and the sample mean, simulations, which I've done before, and approximating normality if n is large. Now look, I'm going to just pause this right, I would like you to pause it right here, right now, and just quickly, I'd like you to take some observations. Okay, so I'd like you to have a pen and paper somewhere, and I'd like you to take some observations, please. So just give me 1 second whilst I find this, get this page up. Okay, so here we have our sampling distribution, and as you can see, I've got something which is not normal. It can be normal if you like. I can make a nice little normal sort of distribution if you like, or close to normal distribution. But let's just let's see if I can try to get a normal, something that's sort of looks normal. It doesn't, not quite normal, but you get the idea. Now, what we're going to do is the whole point of the sample mean is if I was to take a size, say, let's just say 5, what we're going to do is we're going to animate 1, 2, 1, 2, 1, 2, 1, 2. At the moment, I've got here n is equal to 2. So let's do 5 and let's do 10 and let's see the difference. Okay, so I'm going to animate this. Okay, so what we're going to do is we're going to take a sample from the population. Now we know that what the sample mean is mu. Mu is the mu is the same. And if I was to take, oops, let's try it again. 1, 2, 3, 4, 5, bang. 1, 2, 3, 4, 5. Take the average. Done. So we've just done 10. Now I'm going to do it again. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And we've now going to, and we continue to do that. Let's just say we do that for the population 10,000 times. What do you notice? Well, even though this is not a perfect normal distribution, we can say that, first of all, look at this. What do you notice about these things here? If I zoom in right here, the means look pretty similar, don't they? What do you notice about the standard deviation as I increase n, my sample size, my sample size? And what do you notice about, for example, this skew kurtosis? Probably not as much. but it's what is, well, I'm answering the question for you, but you should notice that it's more centralized around the mean. Okay, it is normal. And even if I go ahead and change this to something that's not normal, this is not a normal distribution. Let's go ahead and see if I can go to, now let's try a number which is sort of not quite ideal, which is 2. And let's go from 2 to 20. Okay, so our sample size is we're taking 20 from our population, and we're obviously repeating that. Let's have a look, and we're not going to animate it, but we're going to do it 10,000 times. Okay, so wow. Okay. So as you can see, this is not a normal distribution. Is this normal? No, it's okay, but because it's size 2, it's not really a good indication. We really need to get closer and closer and increase our sample size to something like 5. Let's try 5 and see what it looks like. Let's try 5 and let's do 10,000. That's looking a lot better, isn't it? Okay, but what you can see is, and when they're talking about the central limit theorem, is by increasing this number n from 5 to 20 in this case, we're actually really centralizing closer to the mean. In other words, we're going to have much less standard deviation, much less variance as well. But notice this, that despite the fact that we're taking random samples, the mean, the population mean, still stays the same. So that's what we are always using. Okay, but the standard deviation when we're taking random samples does change when we're taking the sample size of 5, 10, etc. So I hope that sort of making some sense, and it doesn't have to be normal, as you can see here. Okay, so hopefully you can list 5 of the observations. We can first of all say that the population mu, the mean stays the same. What else can we say? That the standard deviation decreases as n increases our sample size. We can also say that there's the central limit theorem. Okay, so in other words, let's just say over here, this could be for n is equal to 20. This could be n is equal to 5. Okay, so still centralized around the mean, population mean, but of course there's that change. And is there anything else you can think of? Well, I guess we could look if you have a look, and you can. It's really not part of the course, but kurtosis changes. Okay, sort of affects like these sort of these two things have different types of kurtosis. Okay, different values of kurtosis, and I guess what we want to say as well is that yeah, the standard deviation does change. Oh, but what we can say is that a non-normal with a reasonable n value becomes a normal distribution. Okay, so there's 5 things that I've noticed. I'm sure you might have noticed some others, but I think that would be a good start. Okay, so now let's start looking, because the population of Australia is around about 25 million, and we can't, of course, do a study of everyone in Australia. It wouldn't make sense. So as I was saying, we have to take samples from a population, and but what we can say is that the sample mean is the population mean. Same thing. How many litres of fuel does the Toyota Corolla need to drive 100 kilometres? You could take 30 samples from the population, and then you can use that that data to come up with, I guess, sort of a confidence interval based on that sample of just 30 from the population. And this is the sort of stuff that happens in real life. This is in business and also like, for example, in let's just say, for example, you have a biotech company and they're doing trials for a drug. And at the moment, I have shares in a company which of course are trying to create a drug for osteoarthritis. And so what they'll do is they'll do trials and they'll take samples of the population, and they will then use that sort of analysis to come up with confidence intervals and all these sorts of things. So this stuff is really relevant. And that's why I was in. Look, it was embedded into the specialist course, but unfortunately nothing really come out. So it is a real struggle to get through the course. As we've sort of discussed. So investigating the sample mean. Let's just work through this together. Theory summary. When mu is unknown, the sample mean can be an estimate. Larger sample size, something, the likelihood of the sample mean being the accurate estimate. A larger sample size, so a large sample size increases the likelihood of the sample mean being accurate estimate of the population mean. The sample mean is a random variable. The random variable, as you've sort of discussed, with the random variable, we were taking five samples and then taking the average, denoted by X bar. Now we've got an example here. The length of time it takes to drive to the city for work on a given weekday is normally distributed with a mean of 40 minutes and a standard deviation of 5 minutes. Simulate a sample where n is equal to 2 and find the sample mean. So look, can I just say that this simulation stuff is all well and good and nice, but quite frankly, we can do this. We can do this in class. But I can just say that if I wanted to do a sample, I can do a number of things. We can do a table, okay, and we could do over here would probably be the best thing. So to simulate the sample mean, like for example here, I've got that there's around about 4,374 students that studied specialist maths. Simulate 100 sample means from samples of size 50. So I'd like you to have a go, but as you can see here, if I was to just simply type in my equation, we've got equals a sequence and then comma mean, rand norm, put in our mean, our standard deviation, our sample size, and then I, 1, and then 100, then you're going to basically get this sort of thing. Okay, now it's in the textbook, and look, I encourage you to try it, but one thing I will say is that it's to deepen your understanding, and I personally think that going on to online Statbook and it can yield exactly the same results. So the theory is that the larger the sample size, the smaller the standard deviation, which we've already discussed. And that is sort of what really brings us to the central limit theorem. Okay, so a little bit of a reflection. Okay, if we take many random samples and average their x bar values, sample means, we will get closer to what? What do you think, Owen? What do you think?
How do you like
at the
them
moment?
apples?
I don't know what's going on here. We will get closer to that's right, the mean, population mean. In other words, the mean of the sample means uh, gives the population mean. Larger sample sizes, something the standard deviation reduces the standard deviation. Larger sample sizes, something the mean. So I guess what we can say is larger sample sizes do not change the mean, but they do centralize a lot of this data around the mean. Okay, so of course the standard deviation is less for these larger sample sizes. So, is the distribution of a sample always normal? Well, we can see from these distributions that that not all of these things are normal. Sample means for samples taken from a normally distributed population. Okay, so we're sort of getting into this whole taking a sample and then looking and analysing this data, and we're going to get to this in a moment. So a sample mean includes the concept the whole sample mean is a random variable, still with its own population mean and standard deviation. We can simulate repeated sampling, as I've shown you, to illustrate the properties, including its mean and its standard deviation. So there's this whole the standard deviation of my sample mean is actually not equal to the standard deviation. It actually relates to this. There's a relationship over here. There's an inverse relationship as n increases, then the standard deviation decreases. All right, and if we take many random samples and average their values, their sample means, we will get closer to the mean. In other words, the mean of the sample mean gives the population mean. Really need to drive this home. Large sample sizes reduces or decreases, reduces the standard deviation of the distribution of the sample means. Larger sample sizes underscore the mean of the distribution. Do not change the mean. Okay, now we're getting into so when we're talking about means, we're talking about if I want the expected value x e to the x bar, that is the expected the expected value of a sample. Okay, so I've got a sample of size n, and of course we can say that e to the x is actually equal to mu, isn't it? Now the variance though is different. So this is very important. This is where this standard deviation of my sample mean is equal to, well, it's not equal to the standard deviation of my general, like we've looked at before. So first of all, the variance of my sample, first of all, that's going to be the variance of, let's call it x1 plus x2 plus x3 plus xn. Now that's over n. Now, if you think about it, if I was to take out 1 over n as a factor and use what I already know, then that squared is 1 over n squared. Variance of x1 plus x2 plus x3 plus xn, for example. Now, as it turns out, this is actually equal to n theta squared. So therefore, we've got n theta squared, n sigma squared over n squared, which is equal to theta squared over n. So I think you might be seeing where this is coming from. So now, if I want the standard deviation of my sample mean, that is equal to the square root of my variance of my sample, which is equal to the square root of sigma squared over n, which is equal to sigma over root n. And that is the most important thing that you can use now. Now, whenever you take a sample of 5, 10, 15, you have to use this. You must. So when you take a sample size, okay, that sample size is going to change the standard deviation, as you've seen. So the standard deviation of my random variable sample mean x is going to change depending on the size. Okay, so I hope that gives you. You don't need to be able to prove that. You won't have to prove that in the exams. But I think that this is probably a good place to stop here, because I do think that look, you know what? Let's do one example, and then let's show you an example on the. Let's do this example, and then we'll do an example from an exam. So the theory is that the expected value of the sample is, when I take a sample of size n, is still mu, but the standard deviation changes as I've just proven. Okay, that is on the formula sheet. That is on the formula sheet, but you should not have to remember that. When working with the normally distributed x's, use mu and sigma provided to calculate the expected value of x bar and the standard deviation. Okay, so it says here the volume of coffee dispensed by a coffee machine is normally distributed with a mean of 280. 280. And a standard deviation is equal to 2 mils. Find the probability, correct the 4 decimal places, that the coffee cup is less than 278. Now, I'm going to say we're going to use X. X is less than 278. Now, you don't have to do anything like, you don't have to do anything crazy here. It's 4 decimal places, so it's a calculator. So what is the thing that we're doing? That's right, it's menu 55. You guessed it, 2. Menu 552. Now, it says here that we're less than 278. So the upper bound is 278. And the lower bound, of course, is negative infinity. Now, you've been given what the mean is. You don't have to do a standard mean of 0. Okay, so that would be just silly to go find your Z values and all of those sort of things. We've got 280 and, so 280. Now, given the fact that the mean is 280, and we know we want to find that it's less than 278, we know that our answer is going to be less than 0.5. What's the standard deviation? 2. It's like, so it's 2 standard deviations away. So it's probably going to be a low value. Okay, it's probably going to be like, 0.04 or 0.03 or something like that. I'm just guessing. Standard deviation is 2. And voila, 0.1587. All right, whilst we're on a roll, let's keep going and let's just do this one and then we'll do the exam question. When working with a normal and distributed, it's the same sort of thing, but this time it says the volume of coffee dispensed by a coffee machine is normally distributed with a mean of 280 and a standard deviation of 2. Find the probability that the mean of the coffee cup is less than 278. Why is that? Looks like it's exactly the same. 280. I want you to have a look and see if you notice anything different between these two. A variation of the same question. What has changed? Well, I didn't actually pause it, but look at this. This one says find the probability to for displace the mean volume of 2 coffee cups is less than 278. So now that we've actually taken a sample of 2 coffee cups, we now need to go ahead and use this baby here. All right, so let's go. First of all, let's find the standard deviation of our sample mean. That's going to be equal to the standard deviation, which is 2 over root 2, because n is equal to 2. That's our sample size. Okay, so we've taken a very small sample. I did say that it's not a very good idea to take a size of 2, but that's what it is in this case. What you're going to notice is that we're not going to get great results from this by taking a sample size of 2. So now what you can see is that I've got now I've got 2 over root 2, or if I go times that by 2 root 2 over 2, that's equal to root 2. That's quite nice, isn't it? Root 2, yeah. Okay, so we've got our standard deviation. So what we've got to do now is we're going to go back and change our menu 55 business, and menu 552. Now be very careful. So this time we're looking at exactly the same thing. We're looking at the mean is less than 278. Okay, so the population mean doesn't change. And what we have is we have to put in our standard deviation. Now, so a population mean doesn't change, but a standard deviation does. Now you've got to be very careful with these. Okay, sometimes you have to do some funny things. So let's do square root of 2. Okay, and as you can see, 0.0787. So therefore, probability that I'm calling it X, but could call it any. The probability that sorry, V for volume, the volume is less than 278 is approximately equal to whatever we had there. I think it was 0.0786. So we've gone from having just taking no samples to 2 samples, and as you can see that we're getting closer and closer to our value there. If I have a look at this, the volume is now normally distributed. Same thing, but find 10 coffee cups. So what we have to do is, once again, all we're going to do is we're going to change that. I'm actually going to change that, press that, and if I've got 10 coffee cups, then my standard deviation is 2 divided by root 10. So I'm going to change that and change that to 2 divided by root 10. It's exactly the same problem, just take into account that n is equal to that. 0.0007, or round it up to 4 decimal places. So the probability that the volume is greater than, less than 278 is approximately 0.0008. So what do you notice about this? You notice that these probabilities are getting less and less and less. It means that we're getting closer and closer and closer because we're increasing the size of our sample. And most importantly, you need to get this in your head that it's the standard deviation over root n. And of course, that needs to be in your calculator. If I just go back to the calculator, that needs to be this guy over here, isn't it? Okay, so as you can see, what has changed? Negative infinity, the lower bound? No. 278? No, that's the upper bound. The mean of 280 hasn't changed. The population mean hasn't changed, but increasing the sample size has changed. So clearly that has changed a lot. Okay, now I did promise you that I'll go through an exam question. Okay, so what we're going to do is I'm going to go straight to, where are we at? Page 18 at the moment. There's some exam questions. Let's go to this one. Okay, I'd like you to have a go at this question, please. Now look, this is the 2018, and the reason why I do it is because it's such a small sample size. Look at this, 10% of the exam. And can I just say that this was a relatively easy question? So the reason I'm showing this to you is because I actually think that in 2008-19 exam, I think in exam one, they're going to ask a very hard question. So try it, pause it, have a go at it. I'm going to go through it in a moment. So I'm going to pause the video right now, have a go at it right now. Okay, so hopefully you've had a bit of a go at this. X and Y are independent random variables. The mean and the variance of X are both 2. So let's write e to the X is equal to 2. Variance of X is equal to 2. Well, the mean and the variance of Y, e to the Y is equal to 2. And the variance of Y is equal to 4. Given that A and B are integers, find the values of A and B if the mean and the variance of AX plus BY are 10 and 44 respectively. So what we're going to do is we're going to sort of find that let's do E to the AX plus BY. That's equal to A e to the X plus B e to the Y. Now we know what e to the X is, that's 2. So we've got 2A and the e to the Y is 2. So that's 2A plus 2B. Alright, so that sounds okay so far. Now it says that the variance of AX plus BY are 10 and 44 respectively. So the mean, and so therefore we can say that 2A plus 2B is equal to 10. So 2A plus 2B is equal to 10. And now what we're going to do is let's do the variance of AX plus BY. And that is equal to, that's going to be A squared times the variance of X plus B squared times the variance of Y using our. So let's go ahead and now that is equal to, what have we said? It says that the variance is equal to 44. Okay, and then the A squared, which we don't know, times the variance of X. The variance of X is 2. So 2A squared plus B squared, which is B squared, variance of Y is plus 4B squared. There we go. Okay, now we've got two equations here. Now, like I've taken my time with this because you can see there that what I think we should do is look at 6 minutes. 6 minutes. So take your time. Don't make a silly mistake. So what I'm going to do is I'm going to say that we're going to say that B is equal to. We could do it in quite a few ways. We could first of all say let's divide both sides by 2. We've got A plus B is equal to 5, which means that B is equal to 5 minus A. Okay, I'm going to call that equation 1 dash. And I'm going to divide both sides by 2 here, which gives us 22 is equal to a squared plus 2b squared. I'm going to call that 2 dash. So therefore, now I want to replace b with 5 minus a. So therefore, 22 is equal to a squared plus 2b squared, which is 2, 5 minus a squared. So therefore, 22 is equal to a squared plus, so that 2, we've got 25 minus 10a plus a squared. And 22 is equal to a squared plus, what have we got? 50 minus 20a plus 2a squared. Now, I'm sure that there's probably a nicer way, but I've just been doing it just off the top of my head. So let's go ahead and let's get this done. 3a squared minus 20 minus 20a is equal to plus 28 is equal to 0. So we want to solve for this. But at the same time, we know that we also know that b is equal to 5 minus a. You probably could have guessed and checked, in all honesty. But so what's the answer? I want you to think, what's the answer? What's the next step? Okay, so look, I could fiddle around with that and get that. As you can see here, from the information given, we needed to have two equations. 2a plus 2b is equal to 10. We had that. We had 2a squared plus 4b squared is equal to 44. The method that I used probably was not the fastest method, which means that, it might have taken me a little bit longer to solve. But as you can see here, guessing and checking, you could have probably got a is equal to 2 and b is equal to 3. Probably could have worked out quite well, actually. I don't recommend guessing and checking, but you've got two equations, and of course, remember that how many solutions are there going to be if they're integers to 2a plus 2b is equal to 10, or a plus b is equal to 5. So the route that I was going down would have got there eventually, but as you can see here, the whole point that a and b are integers really means that you could have actually subbed in. You could have subbed in 1 and 4. Does it work? No. You could have subbed in 0 and 5. You could have subbed in this case, 2 and 3, and vice versa, 3 and 2. So as you can see, the question was done very well. So what does that mean? Well, 2018 exam 1, 10% of the marks was really easy in exam 1. So they might decide this year, they might decide, let's make a tricky question like that one, which is with independence of apples and oranges, for example. So just be mindful of that. A lot of the time VCAR are, based on previous exams and hand performance in exams. This question here was the question which was done the best. It had an average of 3 out of 4. So it's probably fair to say that this year I wouldn't expect anything so easy. All right, I'm going to stop the video there. Now, when we continue, what we're going to be going through is we're going to be going through some more challenging examples, which will finish us up. Okay, so we're going to be going through, so we've been through our sort of distributions and things. So what we're going to start looking at is looking at some of these trickier examples and confidence intervals. And we're also going to be looking at what exactly is a 95% confidence interval. Start looking at confidence intervals on a calculator. And finally, of course, start looking at forming a alternative hypothesis, and actually doing some statistical tests. And of course, there's going to be some errors associated with those. So I think we've got through a big portion of statistics, probability and statistics so far. And I can promise that probably in the next video, things are going to be finished off. So once again, if you like this video, give it a like, email it to a friend or something like that if it's helped you. And I hope that you can, now start thinking about, well, let's start trying some past exam questions for probability and statistics, because we've been through a fair bit.